Hello everyone, my name is Gabriel Bermuda Sellers. I'm in the class Math 130, discussion section 03D for fall of 2022. And I'll be talking about finite difference differentiation, what it is used for, and show an example so you can get the hang of how it works. To start us off, what is finite difference differentiation? To simplify it by quite a bit, finite difference differentiation is a set of formulas that are used as ways to approximate derivatives in ordinary differential equations and in partial differential equations. There are a lot of different finite difference formulas, but the ones I'll be highlighting today are the forward difference formula and with a mention of the backward difference formula and the central difference formula. Forward and backward difference is as it sounds. We use the difference from a point and a point ahead and a behind it respectively and calculate our derivative from it. We get the formula for forward difference by rearranging the Taylor series expansion. After rearranging it, you get the formula that you see on screen. We can get the backward difference formula from a similar manner. Both equations have a big O of the first order, which means that in terms of accuracy, it's not the best. However, both formulas are really easy to do by hand and decode them into a computer. I want to show an example of how someone would solve a forward difference problem. So, in this case, we need to find a derivative of x squared plus 2 at x equals 5 using a small h, which is going to arbitrarily be 0.05. You can go with something smaller if you believe that that would be more accurate. First off, we plug in our function into the forward difference formula. Then we plug in the values for x and h. Lastly, either by hand or using a calculator, solve for the real number. In this case, I got 12.05. Now, if we did the real derivative and plugged in 5, we would get the answer of 12, which means our forward difference formula, while not perfect, get relatively close to the real answer. However, we can get much closer to the real answer. The central difference formula uses a point ahead of a point that we are trying to analyze and a point behind it, both equal distance from our original point, to find a derivative of the point. We get the formula from subtracting the Taylor series for x minus h and x plus h and applying the intermediate value theorem. As you see, compared to forward and backward difference theorems, central difference is a bit more complicated to implement, but this difficulty is worthwhile, as it means that we have a big O of the second order, making it much more accurate than the forward or backward difference. I want to show off another example, this time using the central difference. We're going to start off using the same equation as the last example, with the same parameters. Like with forward difference, we first just plug in our equation into the central difference function. Then we plug in values for x and h. And lastly, using a calculator or by hand, solve it for a real answer, which in this case I got 12. Now, if you remember from the previous example, the real answer we got was 12, which means that this equation got the answer for this problem perfectly correct and obviously was more accurate than our forward difference. Now, this won't always be the case. It just so happens that the central difference got this answer perfectly, but it does highlight how much more accurate it is compared to forward difference. Now, finite difference differentials are not just used in Math 130, they do have uses in real world. They are used in the sciences like physics and geology, especially the more complicated finite difference differentials that I have not gone over today. As for the forward and central difference formulas, they're more historically relevant and are stepping stone for more accurate ways of finding the derivatives that exist today. Uh, However, they are still important in that manner. Thank you all for your time. Have a good day.